Welcome to Research Creations. This video is on the topic of reflection and refraction, how light interacts with and within everything we see. I will be covering the fundamentals of reflection and refraction, explaining what a ray diagram is and how one is plotted. I will also look into the wave speed formula, an integral to understanding how light interacts in triangular prisms and through refraction in general. As a little addition to the segment on refraction, I will introduce two practical analogies in respect to the topic. Before we move on to reflection, I would like to clear up one thing in particular. When a ray of light encounters an object, it either gets absorbed into the object, nestling itself in its energy stores, or reflects off the object, not penetrating or passing through the object, or transmits through the object, when light penetrates into a medium and passes through it. When passing through two mediums of different densities at an angle, we call this refraction. The factors that influence properties such as light wave speed or refraction angle depends on the wavelength of the waves involved and the properties of the two mediums. Now, allow this to be a segue into the topic of reflection. Light is relatively intangible. Thus, in order to visualize reflection taking place, we can plot ray diagrams. An important thing to remember is that the angle of incidence is always equal to the angle of reflection. We'll get to those terms later. To plot a ray diagram, we usually start off with a boundary line. This separates the two materials involved in the setup, in this case, air on top of the boundary and a mirror below the boundary. As you can see, the boundary acts as the reflective surface of the mirror. Then, we can draw the incoming or incident ray. An arrow should be drawn to represent the direction of the ray, pointing towards the boundary. We could draw the reflected ray like this, but it is not apparent to us what angle the reflected ray would be inclined at. This is where the normal line comes in, which is usually a dashed line drawn perpendicular to the boundary. We can measure the angle of incidence, as it is the angle between the normal and incident ray. Let's suppose a value of 45 degrees. Abiding by our previous rule, the angle of incidence is equal to the angle of reflection. The angle of reflection in this case would also be 45 degrees. We can draw a reflected ray, likewise, pointing upwards. A thing to note is that the point where the incident ray and the boundary meet is called the point of incidence, marked here in red. Before we move on to refraction, I'd like to go over the two types of reflection. A material like glass is perfectly smooth, like a perfectly flat boundary. Normal lines plotted across this plane would all be parallel to each other. Thus, all the incident rays will be reflected pointing in the same direction in parallel, leading to a crisp and crystal clear image, like the ones you see in mirrors. This is called a specular type reflection, and is what most people commonly consider to be reflections. Other surfaces, such as a frosted window pane, are relatively rough at a microscopic level, meaning that the boundary is a jungle of peaks and valleys. Since the normal is always perpendicular to the surface, the normals will point in different directions because of the rough, uneven plane. For example, 90 degrees at this point is inclined differently relative to 90 degrees at this other point. Thus, the reflected light rays will also point in different directions, leading to an image that is usually just a blob of light. We call this scattered reflection. Refraction occurs when light waves change direction while traveling through two different mediums. This is because electromagnetic waves, such as light, travel at different speeds through different mediums. Two separate mediums, such as air and glass, are of different densities. In the case of electromagnetic waves, they'll pass through denser mediums slower than lighter ones. When a ray of light encounters a denser medium perpendicular to its entrance plane, the light wave will slow down but travel straight on through the medium, as shown in this diagram. However, when approaching at an angle, the light ray will bend towards the normal, the same perpendicular dashed line as mentioned before. This is called refraction. Next, I would like to cover how to draw ray diagrams for refraction. Let's start off with two different mediums, air and glass. Note that glass is denser compared to air. We should start by drawing our incident ray at an angle. Note that we should always add arrows to represent ray direction. Our next step is to draw the normal, which is a dashed line perpendicular to the glass surface. If the light ray does not encounter any interference, it would continue to travel along the same path, like this. Since the light ray is entering a denser medium, the light wave will slow down and bend towards the normal line. Usually, when accuracy is not a concern, you can draw what's called a refracted ray, somewhere in between this angle, like this. Now, we are on the other side of this piece of glass. Same process, we would have to draw the normal line and picture where the ray would be. Now, since the light ray is entering a less dense medium, it will emerge bending away from the normal, like this. This new ray is called the emergent ray, and should be parallel to the incident ray if both surfaces are parallel as well. The cherry on top is to write down the angle of incidence and the angle of refraction, as you can see marked here. Here's an extension. The angle of incidence and the angle of reflection are directly proportional to one another. So when the angle of incidence is equal to a critical angle of incidence, it would look something like this. Total internal reflection is when the angle of incidence is greater than the critical angle, and the light ray is reflected off the internal surface of the denser medium. We know that the speed of a light wave changes when it passes through mediums of different densities. Let's bring the wave speed formula into the mix, which states that the wave speed is equal to the frequency multiplied by wavelength. Note that the wavelength is the only metric that is independent, while the frequency of the wave always stays constant. Thus, the speed of the wave is directly proportional to its wavelength. This means that different wavelengths refract by different amounts, and we know that different colors in the visible spectrum are of different wavelengths. If we point a beam of white light, which contains all the colors of light in the visible spectrum, towards a triangular prism, each color of light will have a different angle of refraction, resulting in spread out emergent rays. An example of refraction taking place is a common sight for many coastal dwellers. Air and water have different densities, water being denser compared to air. When observing a fish above water, the light reflected off of the fish is refracted when passing through both mediums. To visualize this and determine where the fish would appear to be, we can plot a refraction ray diagram. We can start off by drawing the incident rays, making sure the arrows are pointing up as the light originates from the fish. Then, we plot our normal lines perpendicular to the water surface. Let's imagine where the ray would point. Since the ray is passing into a denser medium, the refracted ray would bend away from the normal. It should look something like this. The human brain processes light as if it were traveling in continuous straight lines. Thus, we should lengthen the ray of refraction by around the same length as the ray of incidence. The image of the fish would be located somewhere around here. Another example of real-world refraction are mirages, occurring on deserts and hot tarmac. Desert air is hot nearer to the ground and cooler higher up, because the surface absorbs heat and heats the air above it. The interesting thing is that an incident ray originating from the tower would be curved, as shown here. So how do we get here? According to particle theory, we know that cooler air is denser than warmer air. We can plot a ray diagram accordingly to better visualize, as shown here. The light ray is passing through denser cool air to lighter warm air. Thus, the ray bends away from the normal. This process repeats until the angle of incidence reaches its critical point, achieving total internal reflection. The light ray points up and reaches the camel. The brain perceives this image as originating from the ground, forming what we call a mirage. Here are the substantives summarized. Normal lines are always plotted perpendicular to the boundary. The angle of incidence is always equal to the angle of reflection. Always use arrows to show ray direction on ray diagrams. There are two types of reflection, specular and scattered. Electromagnetic waves travel slower through denser mediums and vice versa. Angled rays passing from a light to dense medium bend towards the normal. Angled rays passing from a dense to light medium will bend away from the normal. Total internal reflection occurs when the angle of incidence of a ray exceeds a critical point and reflects within the denser medium.